Welcome everyone to another episode of Paper Talk series. Today we have with us Maruti Suryavansi, who completed his MSc from Central University of Karnataka, Kalaburgi, and currently he is working as a PhD scholar in the IPC department at Indian Institute of Science, Bangalore. In today's session, he will be presenting a literature paper which entitled as Optically Controlled Recovery and Recycling of Homogeneous Organocatalysts enabled by Photoswitches. So Maruti, welcome to the talk and the screen is yours.
Thank you, Mahesh. Hello everyone. Today I'm going to present this paper, Optically Controlled Recovery and Recycling of Homogeneous Organocatalyst enabled by a Photoswitches. So this paper came in 2023 and came by the group of G.D. Hahn. So the title of the paper is Optically Controlled Recovery and Recycling of Homogeneous Organocatalyst enabled by Photoswitches. So before going to this paper detail, I'm going to explain some basic so we can understand better this work. So, as a chemistry students, everybody knows what is catalyst. So, catalyst is a substance which will alter the reaction rate by lowering the activation energy barrier. And the catalyst which will take part in the reaction with interacting the reactant, it will convert to the product without consuming itself, it will recover and recycle in the catalytic cycle. So the catalyst will be two types, homogeneous catalyst and the heterogeneous catalyst. And if we see the comparison between homogeneous and heterogeneous catalyst, the homogeneous catalyst, where the catalyst will be completely dissolved in the reaction mixture. As a result, the phase will be same. So the reactant and the catalyst will be in the same phase. And the heterogeneous catalyst, where the catalyst will be in the different phase. As a result, it will be in the different phase and the reaction will happen on the surface of the catalyst. So as an example, in the heterogeneous catalyst, if the catalyst is a solid, the reaction will perform, if you see in this image, it will perform on the surface of the catalyst. So, comparing with the homogeneous and heterogeneous, in homogeneous catalyst, the reaction mixture will be in the transparent and one phase, where heterogeneous one, where the catalyst will be not soluble in the reaction mixture. So, in the homogeneous condition, the usually it will be a faster because the catalyst is completely soluble in the reaction mixture. As a result, it will be a better contact with the reactants, and because of that it will be a faster and better. But in the heterogeneous catalyst, because of this heterogeneous nature of the catalyst and the reaction is performing on the surface only, so for that the only surface energy is required to convert the reactant to product. So for that, this heterogeneous condition one, the reaction will be slower. But as if we comparing the selectivity for the homogeneous and the heterogeneous catalyst, as by tuning the ligand nature of the in the homogeneous condition, where the mostly metal complexes and organocatalysts also are done, but by controlling the ligand nature, we can tune the selectivity by chemoselectivity, regioselectivity, and enantioselectivity can be achieved. But in the heterogeneous one, the catalyst is a insoluble one, and mostly it happens on the surface. That's why it is very difficult to get chemo and regio and enantioselectivity in the heterogeneous condition. And another very important point to notice in the homogeneous and heterogeneous condition, where in the heterogeneous condition, the catalyst is insoluble in the reaction mixture. So after performing the reaction, the catalyst can be easily recycled by just filtering. We can get back the catalyst. But in homogeneous condition, getting catalyst recovering the catalyst, it will be a very difficult, because in homogeneous condition, catalyst will be soluble in the reaction mixture. So another one basic point we should know about photo switching molecule to understand the paper which I am going to present. So the photo switching molecules. So photo switching molecules are those molecules in presence of a light, their isomerization will happen. So their structural changes will observe. So some two examples I give here: a still beam, where in the presence of one particular wavelength, it will switch from trans to cis, and again another one particular wavelength, it will come cis to trans. Similarly, azobenzene as well. So this azobenzene molecule with 365 nanometer wavelength, it will switch from trans to cis, and with 410 nanometer and heating, again it will come back to the original form, cis azobenzene to the trans azobenzene. So the mechanism for this trans to cis and cis to trans conversion is here I wrote. So we are using a light 365 and 410 nanometer. 365 nanometer, when it will get irradiated, there will be a transitions which will be a pi to pi star transition or non-bonding to pi star transition. These electronic transitions will happen. As a result, it will go via two transition state, either a rotational transition state or inversion transition state. So in the rotational transition state, if it is going, if the pi to pi star transition will happen, as a result, a pi bond will become a weaker, and the single bond will be there. As a result, there will be a rotation between these two nitrogen single bond, and it will come to the cis azobenzene. And if it is going via non-bonding to pi star transition, here the non-bonding electrons are now in the antibonding orbital of this pi star. As a result, there will be no electrons on this nitrogen lone pair. So the bond will become it will go in the inversion. So in that way, it will come to the cis azobenzene form. So these are the two ways to get trans to cis. So, and this can be tuned by using electron donating and electron withdrawing group on the ortho substituted of this azobenzene. So if it is an electron donating group, then transition will prefer pi to pi star transition, and it will go via rotational transition state, and this pi to pi star transition will happen by 365 nanometer wavelength. But if it is an electron withdrawing group, so then it will go via non-bonding to pi star transition and inversion transition state. In this way, it will come to the cis azobenzene form. But this non-bonding to pi star transition will be in the visible range. So by using electron donating and withdrawing group, we can tune the switching ability of this azobenzene from trans to cis and cis to trans. So now why I explain these photo switching molecules and the catalyst. If we see in this paper, they of to how to recycle the catalyst in simple way, they did this study. So if we see this oil where the catalyst is insoluble in the reaction mixture. So after irradiating one particular wavelength, the catalyst was insoluble. Now it became the soluble in the reaction mixture. Then it will dissolve and it will perform this catalytic activity. It will convert reactant to product. And after irradiating another wavelength, again the catalyst is regenerating, precipitating. So this is the most simple form to convert catalyst to active form and recycle the catalyst. So there are some other methods to recycle the catalyst, like chromatography technique and distillation or extraction. In that way, if we compare this way, it is a better and sustainable way, because we are using a just external stimuli as a light to recycle the catalyst. So now in this step, how they perform and how they design the catalyst, if we see, so this is the catalyst. If we see in this catalyst structure, so catalyst two ends has a photo switching molecule, which is the azobenzene. And in the middle part, where catalytic active site is this tertiary amine. And there is a one pi spacer they use and this hydrogen bonding unit NH group. So this pi spacer and this NH group is helping to do non-covalent interaction between the molecules. So if we see in this schematic image, so there are molecules which are close to each other. So means the non-covalent interactions are there between these molecules. And this is these four types of pi spacers they use. One is with one phenyl, second one is two phenyl, and this fused phenyl, and this two acetylene group. These are the pi spacers which will do the pi stacking. So that will be the non-covalent interactions to aggregate and disaggregate the catalyst in the reaction mixture. So if we see in this schematic image, where 340 nanometer wavelength, where this photo now 340 nanometer, we know that photo switch molecule this which will switch to the cis form. And now because of this absorption, this for 340 nanometer, this trans azobenzene is switching to the cis form. Now because of this cis form, the structure became distorted and the non-covalent interaction between these two molecules which was supporting to be the catalyst, it was in the insoluble form. So because of this distorted structure, now catalyst will now solubilize in the reaction mixture. And another image, if we see in this is the crystalline form of this first one catalyst, where pi spacer has a one phenyl ring. So with the 340 nanometer, which is a UV range, after irradiating the crystalline form, it is becoming liquefied, and with visible ray again it is, which is the 430 nanometer, again it is reprecipitating precipitated. So which is like before I explain homogeneous catalyst and the heterogeneous catalyst. So here we can tell that this is the heterogeneous catalyst, it is getting converted to the homogeneous catalyst. Again the homogeneous catalyst, again it is getting converted to the heterogeneous catalyst. So homogenation and heterogeneation. So the catalyst phase is changing by using the external stimuli as a light. So now in this work, they studied for these four pi spacer molecules, because these four pi spacer molecules have different pi stacking interactions. So with that, they observed for this one and the two, they achieved a best recyclability between trans to cis and cis to trans, and they gave excellent recyclability. So they continued this two catalyst one and two. So if we see for compound one and two, which I explained recently only with one phenyl and two phenyl, so the isomerization is happening with the 340 nanometer for 30 nanometer. So if we see in this image, where this is for the first, where the pi spacer is a one phenyl ring. Here, the E concentration, if we see 2.9 millimolar, where in the transform itself, there will be some solubility of the catalyst. So because of that, it is a 2.9 millimolar concentration. So after irradiating 340 nanometer, now E form, which is the transform, now it is getting converted into the cis form. As a result, there will be non-covalent interaction will break, and then the catalyst will solubilize in the reaction mixture. If you see here, precipitated around 20.9 millimolar. Similar one, where two phenyl for the pi spacer. Here also the E form, it is around 2.4 millimolar. Again, after irradiating, it came to the 21.2 millimolar solution. So this is the recyclability test they did only for the catalyst. And this is the kinetic study graph. If we see with it, there for the Z form, 10 minutes 10%. So which tells that within 10 minutes itself, we can recycle the catalyst with irradiating 430 nanometer, and this graph tells for the 340 nanometer. Solubility within 10 minutes, almost 70, near 70%, it solubilized. And if this UV graph here, this absorption for the catalyst here around 340 nanometer, which will be the photo switching azo absorption. So this peak, which will be the E form, after irradiating 340 nanometer, this peak immediately suppressed, almost disappear, which tells that the molecule is the photo switching unit in the molecule immediately switched to the cis form. And again 430 nanometer, again it come back to this form. So where it tells that again the conversion from cis to trans happened. For the this is for the first catalyst where pi spacer has a 1 phenyl, which I said here. So this is for the second catalyst, this catalyst where pi spacer has a 2 phenyl. So here as well, this energy for the this energy is corresponds to the azo bond. Here also the energy after irradiating 340 nanometer, immediately the absorption changed. Again irradiating 430 nanometer, again it came back. So and they observe optimize the which solvent is the better one, and they observe that in acetonitrile polarity is best suitable to recycle the catalyst because the cis form of the catalyst in the acetonitrile, if we irradiate 430 nanometer, will try to force come to the E form immediately because of the solvent polarity acetonitrile. So now the catalyst recyclability we studied. Now if we perform reaction and then recyclability if we see, then how it will change we see here. So they perform two types of reaction. This is the base catalyzed Michael addition reaction. So this acetyl acetone one molecule where this CH2 group is CH2 group proton are highly acidic. So this is the catalyst where pi spacer is 1 phenyl. So this tertiary amine nitrogen will upset this proton, and this negative charge will attack on this trans beta nitrostyrene group here, and this Michael addition will happen. So this is the product. So in this step, they saw they saw a recovery rate and how much yield they got. So now Z form where the azobenzene, it will be fully soluble because it is in cis form. So they observed that within 10 hours, they observed more than 90% of yield for this reaction in the first step. And if we see in the E form where molecule is fully aggregated form where non-covalent interactions are uh, uh, non-covalent interactions are there and the catalyst is in the precipitate form. So here after 10 hours also the yield is more than less than 40%, which tells that the active site is fully buried inside the non-covalent interactions. And recyclability test they perform for the 3 cycles. So this green tells the recovery rate of the catalyst. So in the first step, they observe 87% of recycle the catalyst and the yield is almost 90%. And for the second cycle, where the catalyst is reusing for the next step again, here also they observe 84% of the recyclability of the catalyst, and the yield also it's more than 80%, which is around 85%. And for the third cycle as well, the recyclability is almost 80% and the yield as well as more than 80%. So which tells that in the 3 cycles, the active catalyst is getting fully recovered as well, and it is highly active to convert reactant to the product. And the another next step, Henry nitroaldol reaction. Here as well, this nitro group alpha carbon hydrogen atom, which this proton will get abstracted with this tertiary amine, and this negative will attack on this aldehyde group, and this kind of aldol reaction will happen. So in this also, if we see with the 3 cycles, Here they observed 75% of recyclability of the catalyst, and the yield is more than 55%. So which tells that the recyclability is well enough. It is getting almost 75% of yield. And here one more changes they saw, they did to compare. This is the EUV catalyst. EUV catalyst tells the when for this catalyst switched one time to the cis form, and again it came to the trans form. So that cycled one catalyst one is EUV. So that also giving for if we compare for this one and this one, so it is giving comparison is better. So it is giving almost 20% only. So it tells the completely the catalyst is completely soluble in the reaction mixture, then only the reaction perform well. And the conclusion of this paper is, so they successfully developed photoresponsive organocatalysts where the solubility of the catalyst can be changed by just using the external stimuli as a light. So E to Z isomerization they perform by using light 340 and 430 nanometer wavelength, and they recycle the catalyst. And for these two reaction they perform this catalyst, this amine catalyst, and it is giving almost 75 to 87% of the recovery of the catalyst. And over 80% recovery after 3 cycles also they observe for this Michael addition reaction. And the very important thing they studied, the non-covalent interactions are playing very important role to precipitate out the catalyst, where after the switching is happening from cis to trans, the non-covalent interactions will start, then catalyst will reprecipitate, which is the heterogeneation. And two different wavelengths they use to do the switching, and this is the most sustainable way to recover the catalyst. The importance of this paper is a sustainable way to recycle the catalyst, as if we compare the other methods like chromatography technique or distillation or extraction in other techniques, there the recovery will be very less. It will be more very less than this, and which will not be a sustainable way, and there will be a possibility catalyst can decompose. Here the catalyst is completely depend on the external stimuli, and easily it is getting converting from heterogeneation and homogenation. And this is the paper. Okay, thank you.
Nice presentation, Maruti. Thank you for sharing this interesting literature with us. If you enjoyed the session, don't forget to like, share, and subscribe for more discussions from young researchers. Stay curious, and we'll see you in the next episode of the Paper Talk series. Thank you.